tonight. I'm delighted to tell you we have Dr. Sarah Hörst here from Johns Hopkins University. She's currently a professor in the Department of Earth and Planetary Sciences there, and she works to understand the formation and composition of planetary atmospheric hazes. Oh, I'm so jealous. Her primary research interest is atmospheric chemistry. In particular, she is interested in the complex organic chemistry occurring in the atmosphere of Titan. She is also interested in complex organics elsewhere in the solar system, whether they are in an atmosphere or on a surface. So we'll welcome Dr. Hörst, and then if you have questions, I think let me come and give you the mic so that maybe we can keep everybody hearing things in between. So with that, I will turn that over to Dr. Hörst.
Thank you. I have one quick important question. I definitely did not ask how long you all want me to talk for, and a hazard of being a professor is that I could talk for like 10 hours about Titan, which I assume none of you want me to do.
An hour's good for us.
Okay, perfect. Phenomenal. That is what we will aim for and try to save some time for questions. Okay. I have never done this in Google Meet before, so we're all learning together, but when we just did the test just now, it worked okay, but then the Google Meet like disappeared. So we'll see what happens. Okay, we want to share this window. Then we want to do that. Can you see my slides okay?
Yes.
Yes.
Okay, great. I can't see you all at all, which is very disconcerting, but I am just going to talk to these slides, and it's a little bit creepy, but we're going to pretend there's humans there because I can hear you, which is great. Okay. Thank you so much for having me. I'm super excited to talk to you about Titan tonight. Fun fact, I'm actually from Ohio. I was born in Cleveland though. So tonight I'm going to tell you a story, which is the story of what I think of my job as a planetary scientist which is to turn the points of light that we see. Is everything okay?
Yep.
Okay, cool. Sorry. Which is to turn the points of light that we see in the night sky, when we just go outside and look up at the stars, or if you're lucky enough to have a telescope, to take those points of light that we see and turn them into worlds that we study, in the same way that Earth scientists study the Earth, right? To do geology, to do atmospheric science, to do all of those things. And I'm going to tell you that story for Titan, just as kind of a way to tell you about all the amazing things that we know about Titan, but also help you appreciate a little bit about how we got there in the first place. Okay, good. My slides are at least advancing in a way that makes sense to me. So Titan was discovered in 1655 by Christian Huygens, Titan's largest moon of Saturn. Huygens was observing Saturn night after night. He made these lovely drawings. Saturn is a dot with ears, as hopefully you all have seen through a telescope at some point in your lives. And one of the things that he noticed was, looking night after night after night, that there was this dot next to the dot with ears, and it was moving. And it was moving in such a way that it was obvious to him that it was orbiting Jupiter or Saturn. At this point, we already knew that Jupiter had these large moons, and so this wasn't necessarily particularly surprising, I don't think, to him. But nonetheless, this is when Titan was discovered. An important theme for the evening is that if you study the outer solar system, you have to be patient. And so after discovering Titan in 1655, approximately nothing happened for almost 300 years. It is what it is. I don't know what to tell you. So the next thing that happened may or may not even have really been a thing. In the early 1900s, there was an astronomer that was using a telescope in Barcelona, and he made this drawing, and he basically claimed that he saw limb darkening. And limb darkening is something that when we're looking at an object that has an atmosphere, that's something that happens. And it's related to the fact that when photons are trying to go through a solid thing, they can't because it's solid. And when photons are going through a gas, they can because it's a gas, but sometimes the gas will kind of deflect their pathways. And so there's a difference between empty space, gas, and a solid. And we tend to have those three things next to each other when we have an atmosphere. And so he claimed that he saw limb darkening. The jury is still out on whether or not he did. I have heard, however, that he was known to have very good eyesight. And of course, many, many years ago, when our telescopes were not so solid, your own personal eyesight actually mattered for how good of an astronomer you can be. I'm really glad that we have gotten out of that era because I can't see anything. But it's possible that he saw it. He said he saw it. Whether or not he saw it, he was right in suggesting that Titan had an atmosphere. But for the most part, we credit Gerard Kuiper about 30 years later. So in the early 1940s, Gerard Kuiper was looking at the 4 Galilean satellites, so Callisto, Ganymede, Europa, and Io, and then Titan, and also Jupiter and Saturn. And when he did that, he noticed something weird, which is going to be a theme tonight. The weird thing that he noticed was that in the particular wavelength range that he was looking at, which was in the infrared, Titan looked a lot like Jupiter and Saturn, and not at all like Callisto, Ganymede, Europa, and Io. And what he was looking at, what that similarity was the spectral fingerprint of methane. And so he wrote a paper in 1944 that was called Titan, a Satellite with an Atmosphere. And I always tell people that I feel like this paper is missing punctuation, whether it's a question mark or an exclamation point, like something to really hit home that like, this is a really big deal. And hopefully on the next slide, which I also can't see what my next slides are. So this is just it's a choose your own adventure. Yep. Okay. Phenomenal. And so the reason that I think that this title needed punctuation is shown really well in this infographic that was made by Emily Lakdawalla when she was at the Planetary Society. So she made this infographic that she calls the not planets. So these are all of the objects in our solar system that are round or round-ish, that are not planets. Most of them are not planets because they orbit a planet, so that rules them out immediately. Some of them are not planets because they don't clear their orbit, whatever that means. That's a conversation for a different day. Nonetheless, none of these objects are planets. And Titan is sitting front and center, being super weird. So all of the other objects in this image, you see the amazing volcanoes on Io, you see the mare and impact craters on Earth's moon, you see the amazing impact craters on Ganymede, you see Pluto and Charon with their really interesting surface features, Europa with its ice rafts, and then you look at Titan and you don't see anything because Titan's atmosphere and all of the amazing chemistry going on in its atmosphere is in the way. And so Titan is really weird. It's a very unique object in the solar system. This is something that we have known literally since Kuiper pointed his telescope at it and the 4 Galilean satellites, and we're like, well, that wasn't what I was expecting. So stepping back for a second, just to remind us of context, Titan's the largest moon of Saturn. Hopefully you all recognize Saturn. It is the one with rings. Titan is actually kind of in the lower right hand of this image is kind of the little brown dot. This is the moment in any talk when I realize that I need to clean my laptop screen because there are a really lot of dots on my laptop screen, but I'm pretty sure I know which one is Titan. This is a close-up image of Titan that was taken by the Voyager spacecraft. So I told you our theme is patience. So 1655 to 1907 to 1944. 1944, we know Titan has an atmosphere, and then effectively nothing happens for another almost 40 years. So what you're looking at right now is an image of Titan that was taken by one of the Voyager spacecraft as they flew through the Saturn system. I always like to tell people that you too can recreate the Voyager flyby of Titan in the comfort of your own home with an iPhone and an orange. You will get a much higher resolution image, but you will also get approximately as much information as the Voyager team got from this picture. Luckily, Voyager was not just carrying cameras, it was also carrying an infrared spectrometer. And speaking of themes in this talk, another theme is going to be that we like to use infrared photons when we're studying planetary atmospheres. That wavelength interacts with gases very strongly, for better or for worse, when we're thinking about climate change. But Voyager is carrying an infrared spectrometer called IRIS. And this is the spectrum of Titan that was sent back by Voyager. You don't really need to know anything about this because I'm going to tell you what we learned from it. What we learned from it is that Titan's atmosphere is full of organic molecules. So there's ethane, which is C2H6. There's acetylene if you are into welding. There's propane if you want to have your friends and family over to barbecue this weekend. There's hydrogen cyanide if you don't like your friends and family very much. But there's this whole host of what we call organic molecules or carbon-containing molecules in Titan's atmosphere. These two pieces of information, the fact that we couldn't see down to the surface in this image, and the fact that this atmosphere is full of organic molecules was like the most annoying combination of things you could possibly imagine as a scientist. There could have been 10-foot tall Titanians jumping up and down and waving at the Voyager spacecraft, and we would not have known. And so I have spoken to people who were very active in the field at this point, who were members of the Voyager team, and they said basically as the Voyager data were coming down, as they were analyzing them, they immediately were like, we have to send another mission back to Titan. They started planning another mission to Titan. The first mission study to go back to Titan, I think, was published in 1984. So literally just a few years after the Voyager data were sent back down. Again, patience is a virtue. I have no idea what my next slide is. It's really fun. Okay, we're going to pause for a second, and then we're going to talk about what happens next. So as a reminder, Titan's unique in our solar system. It's the largest moon of Saturn, which I've already said, I think 3 or 4 times. Its diameter is about 5,150 kilometers. That makes it larger than the planet Mercury. It makes it larger than our own moon. So even though it is a very small moon compared to Saturn, again, the rock star of this picture that I'm using is Saturn, but Titan is in the bottom right. It is a very large object in the solar system. It has a mass of about 0.0225 Earth masses. If you take that diameter and mass together, you can calculate its density, which is about 1.9 grams per centimeter cubed. That makes about half rock and half water ice. We know from subsequent measurements from missions that I haven't told you about yet that Titan is mostly differentiated, if not fully differentiated. That means that the rock has gone to the core, just like Earth has a core made out of metals and then rock. Titan has a core that's made out of rock. That also means that the surface is actually primarily ice. So when you're thinking about Titan's surface, you're not thinking about rock as we know it, you're thinking about ice. That surface temperature is about 94 Kelvin. Someday I will remember what that is in Fahrenheit. It's like negative 200 something Fahrenheit. It's not even useful to any of us because no matter where you've lived in your life, you can't conceptualize how cold that could possibly be. The surface pressure is about 1.5 bar, so that's 1.5 times atmospheric pressure at sea level here on Earth. And as I've said a few times, it's the only moon with a significant atmosphere. This is something called a phase diagram. We're going to, I don't know who talks to you all. Maybe not so many chemists. So we're going to maybe show some plots that you haven't seen in a very long time, but it's okay. Everyone will live. So this is what's called a phase diagram. It shows the pressure and temperature for different materials and then what phase of matter they are at those different conditions. And this is the phase diagram for methane. Titan's surface conditions are very helpfully labeled with a red T there on the methane phase diagram. And what you'll see is that methane is very close to what's called the triple point of methane. Sorry, Titan is very close to what's called the triple point of methane. The triple point is where solid, liquid, and gas can all exist in the same situation. We are very familiar with living on a planet that is very close to the triple point of a particular molecule. In our case, we live very close to the triple point of water. And that allows us to have water as a liquid, as a solid, as a gas, sometimes at the same time in the same day. I don't know if this, I assume that you all have this happen where you live, but in Baltimore on the East Coast, we have this thing called a wintry mix in the winter, which is a very nice demonstration of the concept of a triple point. But knowing this about Titan is really useful for everything else I'm going to tell you later, because this tells us that methane is capable of existing in all of these different phases, and that's going to be really interesting for the things that are happening on Titan. Okay, so Titan has this dense atmosphere. I said that already. I told you that Kuiper discovered methane around Titan, and that may have given you the wrong impression, because Titan's atmosphere is actually mostly molecular nitrogen. The atmosphere is only about 2% methane, depending on which part of the atmosphere that you're in. The rest of it is molecular nitrogen. But this is the other thing that makes Titan so cool. So Titan is the only other atmosphere in our solar system besides Earth that has a atmosphere that is dominated by molecular nitrogen. So it's the only moon in the solar system with an atmosphere. It's the only other molecular nitrogen atmosphere in the solar system. So already we know that this is going to be something that this is going to be a place that turns out to be very important in informing our understanding of how the solar system works, of how Earth works, a bunch of other questions that we have. These two molecules interact with ultraviolet light from the sun. That light breaks those molecules up. They react with each other to form a whole bunch of new molecules. This is what we call photochemistry. Those new molecules are hydrocarbons, which are molecules that are made out of hydrogen and carbon, because chemists are not creative when they name things. And the other kind of molecules that we see a lot of are what are called nitriles. Those are molecules that are made out of carbon and nitrogen. The other thing that's interesting about Titan's atmosphere, which is a completely separate talk for the most part, is that there's also oxygen-containing molecules in Titan's atmosphere. So there's carbon monoxide, carbon dioxide, and water are the three that we have found. Of those, carbon monoxide is the most abundant, with an abundance of about 50 parts per million. That doesn't sound like much, but that actually makes carbon monoxide the fourth most abundant molecule in Titan's atmosphere. These molecules are actually present in Titan's atmosphere because of a tiny moon you may have heard of called Enceladus, which is very helpfully shooting water out into the Saturn system. Some of it ends up at Titan, does some chemistry magic, and turns into these molecules. But again, that's a completely separate talk. The reason that I bring up the oxygen-containing molecules is the following. All of life on Earth is based on the same small set of molecules. I told you we're going to do some chemistry. So those small set of molecules kind of fall into two big categories. So one category are what we call amino acids. Those are the things that all of the proteins on Earth are built out of. I know protein's really having a moment right now, so you hear a lot about amino acids. And then the other thing are nucleobases, which are the building blocks of DNA and RNA, and also some pieces of some of our energy-containing molecules. Every single thing that is alive on Earth shares those molecules. So they might be important. Those molecules are based on a very small set of the periodic table. You do not need the whole periodic table to make those molecules. You need, for the most part, 4 atoms. You need oxygen, carbon, hydrogen, and nitrogen. If you're feeling really fancy in particular, you would probably ask for some sulfur and some phosphorus, but we're not feeling that fancy tonight. So what we know is that Titan's atmosphere is doing complex organic chemistry. We know that from Voyager. We know that from trying to murder your friends and family by making them breathe hydrogen cyanide. But also there's oxygen in the atmosphere. And so Titan's atmosphere is doing chemistry in which all of the ingredients for the building blocks of life are present. And this is kind of fundamentally one of the reasons why we think that Titan is so interesting. Okay. We're going to go back to our turning a point of light into a world that we study story. So we left off in the early 80s with Voyager. I told you that they started working on a proposal for the next mission to the Saturn system in like 1984. Again, patience is a virtue. That mission, which was eventually called the Cassini-Huygens mission, which was a joint mission between NASA and ESA, which is the European Space Agency, launched in 1997. It was 7 years in cruise to the Saturn system, so it arrived in 2004. Cassini is the orbiter that's shown in the image on this right-hand side. Huygens was the probe that you can see in this same image. That giant gold circle kind of in the middle of the spacecraft is the heat shield for the Huygens probe. The Huygens probe descended through Titan's atmosphere, landing on its surface on January 14th, 2005. Cassini was in the Saturn system for a little over 13 years. The end of mission was September 15th, 2017, when we purposefully, very important, crashed Cassini into Saturn, both to do new science on Saturn itself, which again is a whole different talk, but also to protect some of the moons of Saturn, which we think have the possibility to harbor, if not their own life, to at least be contaminated by life that was potentially carried by the spacecraft. So we had to protect those places, primarily Titan and Enceladus, from any contamination that the spacecraft may have carried. Cassini carried 12 instruments. Huygens carried 6. They were a combination of what we call remote sensing and in situ instruments. So the remote sensings are kind of our instruments that look but don't touch. So our cameras, our infrared spectrometer, those types of things. And then our in situ instruments are the ones that kind of touch, taste, smell. So our mass spectrometers, those types of things. And then just one other thing to mention, because some people don't notice, at the bottom of this image are a bunch of kind of white blobby things, and those are humans in bunny suits. So Cassini was about the size of a school bus. It was not our like cute little rovers driving around Mars. It was actually a very large and impressive spacecraft, for sure. This is what I call Titan's baby picture. This was actually taken before Cassini was in orbit around Saturn as it was approaching. No one has ever done science with this image, as you can tell, because no one has ever bothered to actually, like, I don't know, flat field it or background subtract or do any of the things that you should do to images. This is one where people actually processed it correctly. We're going to talk more about this image in a second, but this is Titan taken in filters that actually can see down to the surface in 2017, shortly before the end of mission. Okay, so we have to do some more chemistry. I'm so sorry. So I told you that we start with nitrogen and methane. This chemistry is driven by photons from the sun, and also some energetic particles from the Saturnian magnetosphere. The main reaction that's happening in Titan's atmosphere is that methane, CH4, is interacting with photons, so light from the sun, and making two molecules primarily. The first molecule is ethane, which is C2H6, and the other molecule is molecular hydrogen, which is H2. The interesting thing about those two molecules is that they end up with very different fates. So when molecules are made in Titan's atmosphere, the chemistry starts very high in Titan's atmosphere, and those molecules end up descending towards the surface because of the motion of the atmosphere. And when you reach Titan's tropopause, it is 70 Kelvin. Basically, nothing is a gas at 70 Kelvin except for like a couple of the noble gases, and that's it. And so everything that comes through the tropopause on Titan condenses, ethane included. So ethane ends up condensing in the tropopause and ends up on the surface as a liquid. The thing about that is that it never gets warm enough on the surface for ethane to go back into the atmosphere ever again. And so once the ethane is on the surface, it's on the surface forever. The hydrogen, on the other hand, goes the other direction. So because Titan's gravity is low, it's about 1/7 that of Earth, it can't hold on to molecular hydrogen, and so the molecular hydrogen escapes, goes off on adventures in space, never to be heard from again. So the major reaction that's happening in Titan's atmosphere is making something that gets stuck on the surface and something that escapes into space and never happens again. And one thing that's really important about this is that this means that the methane in Titan's atmosphere is actually irreversibly destroyed. So it's getting removed from Titan's atmosphere at a constant rate. At its current abundance, it would be destroyed in about 10 to 100 million years with the current chemistry. We think Titan is about 4.5 billion years old, like the rest of the solar system. And so this is a problem that we have not yet solved. But nonetheless, I feel the need to point out. So that is the main thing that Titan's atmosphere is doing, which is actually not particularly interesting. Luckily, it has a bunch of side quests that look like this. There's absolutely no need to learn anything from this slide other than that Titan's atmospheric chemistry is very complicated, and a lot of people have spent a lot of time drawing arrows in PowerPoint trying to understand it. Okay. So once we understand it, we find out that we have some other molecules. I've told you about most of them. These are the 10 most abundant molecules in Titan's atmosphere besides nitrogen, which is its main constituent. And I already told you about most of them. Methane, hydrogen, carbon monoxide, we already talked about. Argon is a noble gas, so it's boring. You can ignore it. Ethane I told you about. Acetylene I told you about. Propane I told you about. C2H4, I can never remember what that's called, but it's fine. Hydrogen cyanide, CO2, we talked about all of these already, but this is just to give you a sense of what the main molecules are that are running around in Titan's atmosphere, most of which we already knew about from Voyager, which turned out to be very disappointing to the Cassini people, but that's okay. Cassini found some other things that are very, very cool. And actually, this forms basically the entire basis of my career, this plot, but right here, which is a weird thing to say, but true nonetheless. So while I was in graduate school, Cassini was busily flying through Titan's atmosphere. And prior to the arrival of Cassini, the heaviest molecule that had ever been detected in Titan's atmosphere was a molecule called benzene, which is C6H6. It has a mass of 78. And very helpfully, the mass spectrometer on Cassini, which was specifically designed to study the chemistry occurring in Titan's atmosphere to answer all of those questions that we had from Voyager, went up to a mass of 100. And so before Cassini got there, if we had kind of imagined to ourselves, as many people had done, what a mass spectrum of Titan's atmosphere would look like, many of them would have guessed something like this. For those of you who aren't used to looking at mass spec, which I assume is most of you, the x-axis is the mass of the molecule or mass to charge of the molecule, and the y-axis is just kind of like the number of them. So this is what we kind of would have thought Titan's atmosphere looked like. And as I just said, the mass spectrometer only went to a mass of 100. So this is as high as it would have gone. Luckily, Cassini was also carrying an instrument called CAPS, the Cassini Plasma Spectrometer, which was designed to study the teeny, teeny, tiny ions in the Saturnian magnetosphere, like electrons and protons. And if you were feeling super, super fancy, like an oxygen ion, but they left it on when they were flying through the top of Titan's atmosphere. And I vividly remember my PhD advisor coming back from a conference and pulling up a plot on his laptop. Someone had pulled him aside in the hallway and they were like, Roger, we have all this data from Titan that doesn't make any sense. What are we seeing here? And he about lost his mind. So this is what the top of Titan's atmosphere actually looks like from the Cassini plasma spectrometer. So the x-axis is logarithmic. Instead of seeing ions up to a mass of about 100, we were actually seeing ions with masses up to about 10,000. So as a reminder, this is benzene C6H6, mass of 78, the largest, heaviest molecule we knew about in Titan's atmosphere prior to the arrival of Cassini. I sat in ChemDraw one day and drew not real molecule. If any of you for some reason are chemists, please don't yell at me. This is not real, but it's just to give you a sense of scale. This is how wrong we were. Okay, that is a molecule that has a mass of 10,000. So we have our little itty bitty benzene, which was the thing that we thought was there, and we have these ginormous other molecules, which is what actually turned out to be there. So benzene has like 6 carbon atoms. Something with a mass of 10,000 has more like 700 or 800 carbon atoms. These are the size of small proteins here on Earth, and these are ions that occur very, very high in Titan's atmosphere, 950 kilometers above the surface. So hopefully you have 1,000 questions now, because that's the correct number of questions to have. But a couple of things that we know. We now know that chemistry is happening very high in Titan's atmosphere, very complicated chemistry. It makes very heavy ions. Your immediate first question should be, what are they? And I have such bad news for you. We have no idea. So this instrument was not designed to do this. It's kind of a miracle, honestly, that we have these data. And so we can't identify the molecules from these data. And as atmospheric chemists, kind of our next tool would be, okay, well, let's do a chemistry model. And again, bad news. So chemistry models, and this is what I actually started my career working on, are really good to like 6 or 7 carbon atoms. So like up to that benzene, but they definitely can't make things of this size. And so we immediately said, okay, that's not the right tool. And so that kind of left us one more tool in our toolbox as scientists, which is to do laboratory experiments, which I really hope is what the next slide is, because if it's not, then I did not set us up very well. Oh, phenomenal news. Okay, so here at Hopkins, I have a lab where we do experiments trying to understand the kind of chemistry that would lead to building these gigantic molecules. And the way that these experiments work is we take simple, abundant atmospheric gases. So if we're running a Titan experiment, we'll do methane and nitrogen. Maybe we'll throw a little carbon monoxide in there if we're feeling fancy and dangerous. We'll expose those molecules to an energy source. In the history of these experiments, which goes back actually all the way to Miller-Urey, if you've ever heard of those famous experiments, literally every energy source on planet Earth has been used. At this point, we mostly use either ultraviolet photons or an energetic plasma. We use both of those things in my lab. That starts the chemistry in the same way that the chemistry starts in Titan's atmosphere and eventually leads to the formation of new molecules. And then depending on the conditions of your experiment, it might lead to a complex organic solid, as shown in this picture, which is suspiciously Titan color, which is very pleasing because this is from a Titan experiment. Once we have that material, which is analogous to these large molecules that we see in Titan's atmosphere, these haze particles that we see in Titan's atmosphere, then we can do whatever we want with it because we're on Earth with a lab. So we can look at the composition. We can look at how it interacts with light, which are called the optical properties. We can they make something called a nano indenter, which is like the world's teeny tiniest hammer. And we can figure out how hard these particles are, which can help us answer a bunch of questions that we have about how they interact both in Titan's atmosphere and on its surface. And so we use these experiments to try to answer questions that we haven't been able to answer from the actual data, which is unfortunate. When we do that, when we look at the composition to try to figure out what these very heavy ions are in Titan's atmosphere, something very interesting happens. That interesting thing is we see a bunch of the molecules that life on Earth uses. So I mentioned nucleobases, which are the building blocks of DNA and RNA. If you can like harken back to, at some point you probably took a biology class and that familiar ATCUG of DNA and RNA, we see those molecules in this material that we make in my lab. Adenine is particularly interesting because adenine also forms a little side piece of a molecule that you may have heard of called adenosine triphosphate, or ATP, which is the source of all of energy for life on Earth. We also, in this particular experiment, saw the 2 smallest amino acids that life on Earth uses, glycine and alanine. And so we see in these experiments that we can make molecules that are interesting for life on Earth. And this gives us the sense that these molecules are likely present on Titan as well. No idea what my next slide is. Let's find out. Oh, it's Titan again. Okay. So we built the Cassini spacecraft. We sent it to the Saturn system. I cheated by showing you what I think is the coolest result, which was like a weird squiggly plot that you may or may not have understood. But now we're going to do the pretty picture version of what we learned from Cassini. So this is Titan again, this time from Cassini. So if you spend $4 billion, you get a higher resolution fuzzy orange ball. You also learn that the Voyager color correction was probably not correct, and Titan's a little bit more yellow than it is orange, but that's okay. We learned a bunch more things though. So we were able to learn more about the haze in Titan's atmosphere. We know that it's made out of a lot of those molecules I talked about before, hydrocarbons and nitriles. You already know what they are, though. You're an expert. I told you already. Amines are molecules that contain nitrogen and hydrogen, and aromatics are any of those things that have like that fun ring structure. They're also called aromatics because they often like smell like something. So your mothballs, most of the molecules involved in cooking, those are aromatic. And they're also present in Titan's atmosphere. Not that you should go cook there. Then if we actually like zoom in and look at Titan's South Pole, one of the cool things that we see is a consequence of that phase diagram that I talked about before. So these are actually methane clouds at Titan's south pole. We know that there are clouds on Titan. We also have seen significant evidence of rain on Titan, made both out of methane and ethane. And so we know from both our imaging data and also from our understanding of physics and that methane phase diagram that methane actually cycles between the surface and the atmosphere, just like water does here on Earth. So, you know, your school kids on Earth learn about the water cycle, and then non-existent school children on Titan learn about the methane cycle. Okay, the cool thing about Cassini is that we learned from Voyager, and so we sent some super narrow wavelength filters on the camera that can see through Titan's atmosphere, and so now we can actually big picture see what Titan's surface looks like. We're going to come back to that in a second. Titan's surface is made out of what I always tell people very scientifically we call the dark stuff and the light stuff. We'll come back to the dark stuff in a second. The light stuff we really don't know anything about, other than we landed in it once. So this is a picture that was taken by Huygens at the Huygens landing site. It landed in the light stuff, not the dark stuff. If anybody is from the desert Southwest, this picture may look a little bit familiar to you. We think that Huygens landed in what is a dry wash during a dry part of the year. So these rocks that you see on the surface are actually technically cobbles. They're about 10 centimeters across. And most importantly, they are rounded. And so that tells us that they have undergone fluvial erosion. The motion of a liquid on the surface over time has eroded these into rounded cobbles. Fun fact, basically every planetary scientist on Earth when this image was returned thought that it was like a screensaver of Mars while we were waiting for the Huygens images to return, including the like literal Titan scientists who were in Europe waiting for the first images to come down, and we're like, why are they showing us pictures of Mars? It's not Mars though. So that's good news. Okay, so we think that that's probably what most of the light stuff looks like. We think that, as I mentioned to you before, that the crust is made mostly of water ice, maybe with like a little bit of ammonia just for fun. The surface has other things on it though. So there is also the dark stuff. So we'll come back to the dark stuff in the bottom half of the image in a second. But if you look at the dark stuff at the top of the image, which is very helpfully, because I'm not a mean person, the North Pole of Titan, what you will see if you switch wavelengths now looking at radar wavelength at 2.2 centimeters is this. Helpfully, our brains are converting this into what they think of as a picture, but this is not actually a picture, it's radar data. When you're looking at radar data, things that are dark are very smooth at the wavelength of a radar. And so anything that's dark in this image is very smooth at 2.2 centimeters. I will tell you right now that the only things that are this smooth at 2.2 centimeters are liquid. And so if you think that these are lakes and seas, you are correct. And then things that are rough at 2.2 centimeters look bright. And so the kind of whiter, brighter stuff is rougher at that wavelength. And so at Titan's North Pole, we have extensive lakes and seas. We have river channels. They look very, very much like Earth. You can't really play this game as much anymore because people have kind of heard the good word about Titan, but 10 or 15 years ago, if you had showed this to an Earth scientist, they would have spent a really long time trying to figure out where this is on Earth, and they would have been very wrong, and it would have been very pleasing. The lakes and seas are actually pretty large, so the largest lakes and seas on Titan are comparable in size to the Great Lakes on Earth. Of course, Earth is much larger than Titan, and so when you're thinking about relative surface area, that gives you a sense that these are very, very large objects. One thing that's cool about them is that this is a place where subsequent chemistry can happen. So we have things that are soluble will dissolve in the lakes and seas and potentially do subsequent chemistry. Things that aren't soluble will either sink to the bottom or end up as some kind of like gross, weird gunk on the surface. We think from laboratory experiments that actually probably both things happen. So those are the lakes and seas. They're primarily located at the North Pole in this point in Titan's history. The dark stuff on the whole rest of this image, so everything from the mid-latitudes in the north to mid-latitudes in the south and encircling the entire moon all the way around are extensive dune fields. This is what they look like in Cassini radar. They are very similar in shape, size, whatever you want to call it, to a sand sea in the Namib Desert here on Earth, which I was very, very lucky to get to see in person this past fall. I told you that all the rock on Titan went to its core. These sand particles are not made out of rock. They're made out of organics that were made in the atmosphere. Please do not ask me how we turn that into sand-sized particles. I had a grad student spend her entire PhD trying to figure it out, and we still have not figured it out. But those sand particles are made out of organics. Last place we're interested in, impact craters. There are very, 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 very few of them on Titan. Titan's surface age, best estimate recently, is about 300 million years. That makes it one of the youngest surfaces in the solar system. There are very few impact craters. The reason that we're interested in impact craters is because the organics in Titan's atmosphere have never met a liquid water molecule in their whole entire life. But when there's a large impact into this icy crust, all of that energy goes into melting that water and generates an impact melt pool that can last for tens of thousands of years. All of those organic molecules that have never met a water molecule before get super, super excited to do some really cool chemistry that we call hydrolysis and make a bunch of molecules that we think are important for life. And so that's one of the places that we're really interested in going. This particular impact crater that I just showed you is called Silk Crater. Silk Crater is going to be very important to us momentarily. No idea what the next slide is. We're skipping that one. We're not skipping this one, though, because I think everybody on Earth needs to see this picture. If you haven't seen this image before, this is the first sun glint off of another world. Cassini captured sunlight reflecting off of a lake at Titan's North Pole. That particular lake actually wasn't named at the time. Lakes on Titan have to be named after lakes on Earth, and so this lake was named Jingpo Locus, which means mirror lake, which I think is really cool. And this is my favorite image from the entire mission. Okay. So I told you that Titan has all of the ingredients necessary for life, which is one of the reasons why we're so interested in it. We have energy, both from the sun and also from all of the molecules that are made in the atmosphere. They carry their energy down to the surface. I have not stopped talking about organic material basically since I started this talk, so we've got a bunch of that. We have liquids. I've told you about them. We have a subsurface liquid water ocean, which I didn't tell you about until right now, but we have that, so now you know. We also, as I mentioned, have liquid water available whenever there's impacts into the surface. But we also have this methane cycle that I have told you about. We have methane cycling back and forth between the atmosphere and the surface. We have lakes and seas. We have clouds. It rains. There's going to be rainbows. You can like envision walking on the beach on Titan and squishing your toes in the sand. If you find yourself there, please let me know. I have so many questions. But the point is that on Titan alone, we can study this chemistry that I have been kind of forcing down your throat this whole time, but in the context of this moon that is doing all of this Earth stuff. It has clouds, it rains, it has river channels, it has sand dunes. Like it's doing Earth things with a bunch of life chemistry, and like it seems like we should probably go check that out, right? At least that was my thought. Okay, so what's next? So we're just going to do this for like 5 minutes and I'll take some questions. So what is next in our now long-standing, many hundreds of year mission to turn Titan from this point of light into a world is a mission called Dragonfly. So Dragonfly is a mission to explore Titan's prebiotic chemistry and its habitability using a mobile platform. We are like effectively a flying Mars rover, basically. We're the same size, we're the same mass as a Mars rover. We are carrying a kind of comparable number of instruments, but we just fly because it makes more sense. So Titan's gravity is about 1/7 Earth's gravity. Its atmosphere is 4 times denser because the pressure is about the same, but it's much colder. And that means that it's actually easier to fly on Titan than it is on Earth. Titan is the easiest place to fly in the solar system. If you personally found yourself on Titan, and again, if that happens, call me. I will give you my cell phone number. Bring some balsa wood, duct tape it on your arms, flap those wings that you just made, and you will be able to fly under your own power. It is that easy to fly on Titan. And so we're taking advantage of that with this mission to be able to access all of these different interesting geologic settings that I just told you about. we have kind of three big picture science goals, which should not be surprising to you at this point. We have this really interesting prebiotic chemistry that we want to study. We have all of these environments that are potentially habitable that we want to understand. So we're going to do things like measure atmospheric conditions, look at processes that mix organics with that surface liquid water, like I talked about before. And also, although Dragonfly is not a life detection mission, which is very important for me to say so that I can keep my job, we will be searching for biosignatures. So we will look for chemical evidence of water or hydrocarbon-based life while we are trying to understand that prebiotic chemistry. Our initial landing site is going to give us access to a whole bunch of these different places. So this is Salt Crater, like I showed you before. We're going to actually land southeast of Salt Crater in that dune field. And the reason is that this is like the best image that we have of Salt Crater. We don't have like, meter or sub-meter imaging like we have on Mars. And so we have to use physics to find a safe landing site. I promise the picture on the right-hand side is going to make sense in a second. So what we're going to do is we're going to go land in one of the interdune regions. So the spaces between the dune fields, because physics tells us from everything we know from Earth and Mars and Venus that interdunes regions are flat and boring. And flat and boring is where you want to land your spacecraft for the first time. They're so flat and boring, in fact, that the 43-year-old woman on the right-hand side of this picture can do a handstand in an interdune region in the Namib Desert. So that just gives you a sense of how boring interdune regions are. They're a very safe place to send your spacecraft. And so that's where we're going to land Dragonfly, in an interdune. Then we're going to start flying northwest up into this impact crater deposit and then eventually into Salt Crater so that we can study all of this different material that's located there. This slide is really boring actually, but it shows you where we're going to land. And basically says that we're going to be, exploring Titan for a little over 3 years. That gives us about 70-ish Titan days of science operations and is going to allow us to explore something like 30 unique landing sites over those 3 years. We carry 3 instruments. One is called DRAMS, which is the Dragonfly Mass Spectrometer. That's really our workhorse instrument. We are very excited about the chemistry. Hopefully that has come across through this talk. If it hasn't, I haven't accomplished anything. And so that's really going to be our main instrument, trying to understand the complex organics that are now on Titan's surface, but were made in its atmosphere. To do that, we're using another instrument called Draco, which is the drill for acquisition of complex organics. And so attached to one of our skids is a drill which will be drilling not super deep. We're not drilling for oil here. We're just getting into the near surface, just a few centimeters, to then sample that material into the spacecraft and put it into the mass spectrometer. Another instrument that we have is called Dragons, which is Dragonfly Gamma Ray Neutron Spectrometer. Dragons is my favorite named instrument ever in the history of planetary science because I get to talk about dragons on Titan all the time, which is pretty cool. I realize that the lights just turned off. If you can see my video, hold on for 1 second. Computer, turn on living room lights. It just told me to go to bed. Sorry. That's our Sarah, it's time to go to bed alarm in my house. So we could talk about dragons on Titan. And there's like a whole bunch of dragons acronyms that involve fire and stuff because we're super nerdy. But the cool thing about dragons is that gamma ray neutron spectrometer lets us figure out the bulk composition underneath us, just kind of wherever we're sitting. We don't have to drill. We don't have to do anything fancy. We just sit there. Dragons measures gamma ray neutrons that are coming off of the surface and tells us we're mostly over hydrogen and oxygen in a ratio that is suspiciously specific to water, or where there's also a bunch of carbon underneath us. And we're also hoping, depending on how cooperative Titan is, which it's frequently not, that we might also get some information about are there organics under the water? Is there water under the organics? What's the layering structure, that kind of thing. But it's going to be really helpful to us because there are what we call consumables on DRAMs. So things we can only do a certain number of times before we can't do them ever again. And so we don't necessarily want to take DRAM's measurements at every landing site, but we can take Dragon's measurements at every landing site. And so that's going to help us say, okay, big picture, the composition under us is exactly the same as the last place. So maybe we don't want to drill here because we're just going to find similar material. DragMet is our geophysics and meteorology package. It's kind of a weird combination of things, but they're combined because it's a whole bunch of sensors that are located all throughout the spacecraft, and they use the same brain. So it's things like a methane sensor, our pressure sensors, our temperature sensors, our wind speed sensors, seismometer. We're looking at weather, and we're looking at whether or not there are Titan quakes underneath us to help us understand what might be helping with the near subsurface and also the subsurface liquid water ocean. And finally, our last instrument is DragonCam, which is all of our cameras, from our big picture cameras that are big picture, from our cameras that are taking our imaging as we're flying, all the way down to our basically like microscopic imager that can do things like look at the tailings pile when we drill to try to figure out, like, is that too gooey? Because we don't want to put anything gooey into the spacecraft. And so we'll be able to look at things in a variety of scales from DragonCam. We're going to skip that. We're going to skip that. I already told you about that. I already told you about that. We're skipping that also. We're not skipping this. People always want to know, Sarah, where's Dragonfly at right now? Man, do I have just like such exciting news for you. So we are currently in integration and testing. We moved into integration and testing in January. So they have been building the spacecraft for about 7 months now, which is so cool. This is an applied physics laboratory mission, and so the spacecraft is being built about 30 minutes from work for me. I do occasionally get to go down there and just like stare at it in awe, and I definitely don't cry every time I see it or anything. I'm a totally normal human. We launch. Our launch window opens the first week of July 2028. So we are less than 2 years from launch, which is a completely crazy thing to say at this point. Again, patience is a virtue. So we arrive at Titan in 2034. So we still have a little ways to go. I have no idea what my next slide is. Oh, it's a little video. We'll see if that works. And then this is the last thing, I think. Oh, but this is a new fancy video, so I don't know what I'm going to say. But so we get to Titan. That's our back shell. We're going to descend through the atmosphere. I don't know what happens next. Oh, now we're looking at the heat shield. So we're looking at it from the other way. So we're going to ascend on parachute until we're about 1 kilometer above the surface. I forget what our final number is, but we're about 1 kilometer above the surface. We descend on parachute. We drop down a little bit. We drop our heat shield. We drop down a little bit off of the back shell. We spin our rotors up, which this whole thing is just very intense. This is going to be the most stressful day of my entire life. We spin our rotors and then we just get dropped. So to prevent the parachute from landing on top of us, we have to fly away from it. And so we fly down to the surface from about 1 kilometer. The good news is that by the time we land for the first time on Titan, we already know that we know how to fly. So we're going to fly to our first landing site. We will spend a bunch of time at our first landing site because we have to make sure that all of our instruments can work, exercise those cameras, make sure the drill works okay. Metaphorically, I guess, stretch our legs after our long voyage. After that, we will send back all of those amazing data. Our communication system is direct to Earth, so that giant circle that you see on the back of the spacecraft is our high gain antenna. We don't have any way to relay data back to Earth like we do for Mars, so we have to send it directly back to Earth from the spacecraft. This is us landing at our first landing site. We are anticipating probably kicking up dust. We actually have some cool experiments designed to use Dragonfly to make like a tiny wind tunnel to understand how sand particles move on Titan, which is pretty exciting. Yep, there goes our high gain antenna. It's going to find Earth and be like, I made it, guys. All of your hard work has paid off. And then once we are done at our initial landing site, we're going to pack our high gain antenna up back where it goes. Yep, there we go. And then we're going to fly off to our next landing site. And we're going to do that over and over again a bunch of times for at least 3 years. I'm pretty excited about that. And I lied. I think I have one more slide. Okay. If you are super excited about Titan, I have two phenomenal book recommendations for you. They were both written by Ralph Lorenz, who is a member of the Dragonfly team. The first one is Lifting Titan's Veil, which was written before Cassini, and it's kind of all of the history of Titan exploration up until Cassini launched. And then he wrote another book called Titan Unveiled a few years into the Cassini mission that talks about how Cassini got built and the science that was done by Cassini. I assume at some point he will be writing a book about Dragonfly, although I have not asked him. He doesn't pay me to tell you all of this, but he really should. And then the last thing before I take any questions, if you have any questions that I do not answer tonight, please feel free to email them to me. And also please just understand that I will absolutely reply to your email at some point, and it will either be 1 minute from when you send it or sometime next year. And I make no guarantees about which of those things it is, but I promise that I will answer it. And with that, I would love to take questions, but I'm going to stop sharing my slides because it weirds me out that I can't see all of you. Okay, now I have to find you again. There you are. Okay, that makes me so much better. It's weird to not see while I'm talking to you. Does anybody have any questions? Okay. Everyone's like, Sarah, we want to go to bed.
Anybody have questions? Or I'll start with one. Not knocking Titan at all, but I thought Triton, Neptune's moon, I thought that had an atmosphere as well.
Yeah, so Triton, so we do have a couple of other molecular nitrogen atmospheres in the solar system. So you're right, Triton has an atmosphere, Pluto has an atmosphere. That starts to really stretch our definition of atmosphere because they are very, 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 very thin. And so the chemistry of those two atmospheres, Triton and Pluto, is actually really interesting to me and something that we study in my research group because those are both nitrogen, methane, carbon monoxide atmospheres like Titan. But they don't do a lot of atmosphere things. Like it's not going to get really windy. They're not going to have the circulation of an atmosphere the way that we tend to think of it because they just aren't very thick. And definitely can't do things like support some type of liquid on the surface because the pressure is so low.
Okay. Anybody else? Okay. Right, you want to do the to the whole room. Here you go.
You mentioned that the atmosphere of Titan has some very high molecular weight compounds. Are those compounds primarily like long chain alkanes, or are they aromatics with things like benzene rings in them?
No idea. Probably both.
Okay.
When we make the materials in the lab, we definitely end up with a mixture of both. We tend to see a lot of the rings and the kind of more strongly bonded together stuff, but our energy environment in the lab is also probably favoring those things. So if I was a betting person, I would bet pretty strongly on a mixture of all of the above, and that's definitely what we have designed the instrument to be able to analyze. Is basically like any organic chemistry word that you can think of. We're not married to any idea because we haven't actually identified any compounds heavier than, like, if we're being very generous, we're pretty sure there's toluene in the atmosphere, which has a massive 91 or 92. But other than that, we haven't identified anything bigger than that, and so we don't know.
Thank you.
NASA funding and research or other?
Here we go. Be easier with that.
Is NASA funding the research, or is the funds coming from another source?
So Dragonfly is a NASA mission. So it's funded, well, it's a little complicated. It's funded primarily by NASA. We have some really strong partners in the European Space Agency. So particularly the French Space Agency is providing some really important components of our mass spectrometer. So we work very closely with them. And then the seismometer is actually being provided by the Japanese Space Agency. And so this is a very international mission, just like Cassini was. And we have contributions from other space agencies, but it's primarily being built and funded by NASA.
How is power generated on the Dragonfly? And then is there any concern with near surface winds like dislodging the spacecraft?
Yeah, those are both phenomenal questions. So I'll answer your first question first. So Dragonfly is powered by a radioisotope thermonuclear generator. So an RTG, just like Curiosity and Perseverance on Mars, just like the New Horizons spacecraft to Pluto. It's kind of our standard outer solar system thing. We can't use solar panels at the surface of Titan. Only about 10% of the light that reaches Earth reaches Saturn. And then only 10% of that light that reaches the top of Titan's atmosphere actually reaches the surface. And so we have an RTG that trickle charges a battery. Dragonfly is about the size of a car, and it is almost entirely battery. So we're basically just very, very slowly charging this battery that allows us to fly over time. Your second question was about near surface winds. Titan, as far as we know, from the very few direct measurements that we have and a really, really lot of super fancy atmospheric modeling by people who I hope are smarter than me, has very low wind speeds in general, both near surface and basically as high up as we're going to fly, which is never going to be more than like that, initial kilometer that we flew from at the beginning. There are periods of Titan's year, which is about 30 Earth years, that we think do have stronger winds, but we will not be there then unless the mission lasts for a very, very long time. And so we are expecting the weather to be extremely boring. No rain, no wind, nothing that can cause us problems. But that's part of the reason why we have those sensors on DragMet, to make sure that we're getting a really good weather report before we fly, and also potentially while we're flying. And so Dragonfly has the ability, when when it is supposed to like wake up one morning and go off on a flying adventure, to measure the weather and go, no, I'm not doing that. Hopefully it doesn't do it just because it's tired. Like, I'm spicy. I don't want to do this today. I'm going back to take a nap. You guys go do something else.
What's next? What's next?
What's next for Titan?
Yep.
Dragonfly, hopefully. After that, I don't know. One of the things that's interesting about the outer solar system is that, for better or for worse, we don't get to go there very often. So in the Titan community, we tend to think of a career as spanning about 2 missions, is kind of the cadence that we've had so far. So if you go with that math, Dragonfly is my last Titan mission of my lifetime and career. I sure hope that's not true, but history says that it probably is. There are other mission concepts that people have been thinking about. There are other mission concepts that have been proposed. So one question we get asked all the time is about going to lakes and seas. So Cell Crater is equatorial. I told you the lakes and seas are at the North Pole. We never would have been able to send Dragonfly to the North Pole. Titan is tilted. It has about the same obliquity as Earth. And so we have to talk directly to Earth. I said that already. So when we arrive, Titan's North Pole is in darkness. It can't see Earth. So we never would have been able to send Dragonfly to the lakes and seas. But people have proposed missions. There was a mission called Titan Mare Explorer that was proposed to go to the lakes and seas a little over a decade ago now, maybe 15 years ago. I think that would be really cool. And I am suspicious that the next Titan mission that actually flies, whenever that may be. Again, I'm not optimistic that it will happen in my lifetime, but I think that probably the next Titan mission after Dragonfly will go to the lakes, whether it's a boat or like I don't know. I'm having trouble thinking of like amphibious vehicles, but like maybe something that can be like a car and a boat, like a transformer. I don't know. But there are people who are working on developing the technology for doing like a Titan submarine or Titan boats, that kind of thing. Just because like we should probably send a fish finder to Titan just to double check.
Anyway.
And I'm sort of curious about the low temperatures, sort of when you were doing the synthesizing of, or sort of trying to recreate the organic molecule process. So was that done at sort of the negative 290 Fahrenheit, or?
Yeah, my lab goes through a pretty intense amount of liquid nitrogen. We had another delivery this morning, and I'm pretty sure Airgas is just like, why do these people buy so much liquid nitrogen from us? So we do everything at temperature. Yep.
And so like that's why those molecules were not discovered earlier, is just because you have to Because you're introducing them to plasma. You're introducing them to plasma while they're at negative 290 or -1 Kelvin.
So reason why they, not to get like too spicy or like to my own horn, the reason that people didn't find those molecules in those experiments previously, to be completely honest, was because they were not looking for them. When I wrote code to look for those molecules in the data, I found them almost immediately. So they were definitely present in, I am certain, present in decades worth of experiments, and people just never found them.
Oh, so it makes a bunch of other stuff as well?
Oh yeah. I mean, we used to, back when Twitter was a thing, we used to play a game where people would like suggest a molecule to me and I would go look in the data to see if I could find it. And this was when like Breaking Bad was pretty popular. So one day someone was like, "Hey Sarah, is there methamphetamine in your material?" And I was like, I don't know. And I went and looked and like, yeah, I guess so. Don't tell people I've been making methamphetamine in my lab, but like, whoops. We find all kind, like we found like there's a bunch of caffeine, like if you need your coffee fix. I mean, like any molecule you can think of is in this stuff. There's like tens of thousands of different kinds of molecules.
And then mass spectrometers, do they need to heat up to operate properly?
Yeah, that's a really good question. I could like pull up a bunch of slides and we could like really get nerdy about drams.
So is that part of the consumable on the mass spectrometer on the Dragonfly?
Yeah, so we are trying not to heat our samples. So one of our requirements, and there's like one of the things I'm sure the drill team absolutely hates us, because one of our requirements is that the samples are analyzed at almost ambient Titan temperature, so almost 90 Kelvin, which means that however the drill gets them into the spacecraft, they have to still be almost 90 Kelvin. Not quite, but almost. And so then when they get into the spacecraft, we actually try really hard to avoid heating them at all. We do have a pyrolysis mode of the mass spectrometer. It seems like that's something that might be meaningful to you. For everybody else, that just means that we heat them up until they go into the gas phase. But again, we're going to try not to use that. So our main consumable actually is what's called, this is very nerdy, I'm so sorry for those of you who aren't chemistry nerds, but it's what's called a derivatization agent. And basically what that means is that we put this chemical in with the stuff we're trying to analyze, and it makes it much easier to make it go into the gas phase. Things have to be a gas to measure them with a mass spectrometer, but we're starting with solids that we just drilled from the surface. And so we're mostly exposing them to a derivatization agent so that we don't have to heat them so much. This is a technique that has been used very, very successfully on the Curiosity rover. And we have what's called heritage. So our instrument is the direct descendant, the daughter, if you will, of the mass spectrometer on Curiosity. And so our main consumable for the mass spectrometer is these little cups of derivatization. It's like a really hard word to say at 9:20 at night. Derivatization agent. And once those cups are used, the derivatization agent is gone. We can reuse the cups themselves to like store sample, but then they're contaminated and we don't have the derivatization agent anymore. And for various chemistry reasons, we're actually carrying multiple derivatization agents. And so that particular consumable is like very precious and important to us because we can't do that type of measurement once we're done. We can still use other modes of the instrument. We also have what's called laser desorption. I don't know if this means anything to you or not, but we can also shoot a laser at the samples and use that to make them go into the gas phase. All three of those techniques, heating it with pyrolysis, shooting the laser at it, and using derivatization, access slightly different chemistry. And so it's both kind of practical in the sense that some of them are consumable, some of them aren't, some of them are destructive, some of them aren't, but also practical in the sense that they help us analyze actually completely different molecules and is going to give us a really good picture of what we're seeing on Titan. And I'm really sorry for the people that was really boring for, but I really love mass spectrometry. So hopefully some of that made sense.
Any other? Yeah.
So is there a concern with contaminating Titan with Earth material?
Yeah, absolutely. So maybe you know this, maybe you don't, but NASA has an Office of Planetary Protection. I assume at least like 83% of you are Star Trek nerds, so hopefully this analogy will land. But NASA has kind of its own prime directive. So the prime directive in Star Trek is that, you know, you don't like go and just like show up in your Star Trek clothes and are like, hi, we're creatures from other places. How's it going? And so NASA's kind of prime directive is that we don't forward contaminate the places that we go, particularly if we think that they're places that could either have their own life, or places where Earth life could get toehold because there's liquid water, for example. And so every NASA mission works very, very carefully with the Planetary Protection Office to come up with a planetary protection plan. This is one of the reasons why you see the spacecraft getting assembled in clean rooms with the people in the bunny suits. It's to make sure that Earth bacteria, Earth creatures don't hitch a ride and go to the place that we're going. And again, this is actually why we crashed Cassini into Saturn. And so Dragonfly has a very very thoughtful and extremely detailed planetary protection plan that was worked out with the NASA Office of Planetary Protection, and involves things like constantly, like NASA employs biologists who come and like swab the spacecraft and then like culture it. And then if the stuff grows, then people get yelled at and you have to clean the spacecraft again and do all of those things. So we're trying to be as careful as we can. But you know, that's part of the mission and part of all of the hard work that goes into building these spacecraft.
Okay, I think that's probably a pretty good place to stop. Sarah, with your permission, I send out notes from this meeting out to people. If I include your email in case they come up with questions on the way home, that
that's
they
perfect.
can send those to you?
Yep,
Sound
absolutely.
good?
Yep, that's wonderful.
Okay. Well, then, thank you very much. We very
Thank you so much for having me. I really appreciate it. I know it's late, and I really appreciate your attention and your phenomenal questions.
Thanks again.